Modern theoretical physics is defined by a deep tension. The smooth, continuous geometry of general relativity contradicts the discrete, probabilistic nature of quantum mechanics. Einstein's field equations provide extraordinarily accurate descriptions of macroscopic gravity, yet they suffer mathematical breakdown in regions of extreme density. This loss of predictivity inside black holes or at the Big Bang suggests that the four-dimensional spacetime manifold is not a fundamental constituent of reality. Instead, diffeomorphism invariance and the metric tensor are effective coarse-grained approximations emerging from a primitive high-energy substrate. Diffeomorphism invariance is the mathematical property ensuring that physical laws remain consistent, regardless of the coordinate system used to map them. To resolve the infinities of classical singularities, physics must move past the smooth continuum and rebuild spacetime from a discrete, granular foundation. The variable slice density, or VSD model, offers a framework to synthesize these domains into a single emergent structure. The model is rooted in the eternalist block universe of relativity, where past, present, and future coexist statically. In this ontology, the flow of time is a subjective psychological construct rather than an objective feature of the universe. While the traditional static block universe cannot easily incorporate quantum unpredictability, the VSD model integrates the many worlds interpretation. The many worlds interpretation posits that the universal wave function evolves unitarily without collapse, leading to the proliferation of independent histories. Under absolute decoherence, the universal wave function dissociates into states possessing definite classical 3D geometries. This process occurs without the need for a dynamic wave function collapse. This comparison shows that VSD frames physical dynamics as a timeless traversal of varying geometric density, rather than as geometric curvature or probability transitions. VSD defines the universe as a static, branched multiplicity of pre-existing 3D configurations populating a fixed 4D architecture. Applying a block universe to general relativity is challenged by lacking a preferred time parameter. Diffeomorphism invariance allows arbitrary mathematical slices of the manifold, meaning there is no unique universal now. VSD solves this by utilizing the time-like eigenlines of the Ricci tensor. The Ricci tensor is a complex mathematical object representing the specific part of spacetime curvature, determined by local matter and energy. These eigenlines represent the average motion of all matter and radiation at each point. They correspond to the local rest frame where the cosmic microwave background dipole is completely zero. These absolute paths serve as the integral paths of the time-like eigenvectors, establishing a non-arbitrary vertical axis through the 4D volume. Proper time is calculated by integrating exclusively along these fundamental world lines. This provides a non-local mechanism to define unique surfaces of constant time, mapping VSD to the Arnolet-Disser-Misner decomposition used to study the dynamics of space. These eigenlines provide the strict geometric gauge needed to calculate an objective slice density across the manifold. Within the ADM 3+1 formalism, the lapse function, denoted by the Greek letter alpha, determines the rate of proper time flow relative to coordinate time. A central goal of VSD is proving that this lapse function is uniquely determined by the quantum configuration density, ρ. The lapse function is inversely proportional to slice density. Near a mass, high density forces the lapse toward zero. Observers possess a fixed experiential budget of configurations per coordinate time. Traversing dense regions mechanically stretches subjective experience across bunched slices, generating perceived gravitational time dilation. VSD defines slice density by reinterpreting the Born rule. The square of the wave functional amplitude becomes the literal frequentist density of coexisting 3D states. This density satisfies normalization conditions to preserve the total count of spatial states without the need for traditional wave function collapse. Gravitational force is a static structural gradient, where high configuration density throttles the passage of proper time. We apply this density correspondence to the Schwarzschild metric, describing empty space surrounding a spherical mass. The focus is on the geometry as the circumferential radius approaches the Schwarzschild radius, the event horizon of a black hole. As the observer nears the event horizon, the structural bunching of slices scales toward literal infinity, driving the lapse function to zero. This infinite bunching explains why distant observers see falling objects freeze at the horizon. They traverse a maximal information boundary. In VSD, black hole horizons are discrete information bottlenecks, where the smooth continuum limit fails and the discrete substrate takes over. Beyond stationary mass, we must examine how moving objects interact with this static 4D block. While the block universe is ontologically static, its branching multiplicity is structurally asymmetric based on direction. An observer's velocity relative to the local Ricci eigenlines causes an anticipatory splitting of time slices in the direction of motion. This defines the effective spatial metric. Spatial distance equals the branching factor, b, multiplied by coordinate distance. This forward multiplicity forces moving objects to traverse more available paths. Requiring extra configurations to cross a single coordinate unit physically elongates the spatial path. A bounded coordinate velocity forced to cover this structurally elongated path physically reproduces Lorentz contraction. Lorentz contraction is the relativistic effect where a moving object's length is measured to be shorter than its proper length. This kinetic elongation remains consistent with many worlds, as branching ripples out along null cones, ensuring anticipatory splitting never violates causality. This chart compares velocity and branching multiplicity. The universal speed of light, c, represents the absolute physical saturation of the underlying substrate's branching capacity. Special relativity's rules act as hard structural limits on how fast quantum information can organically proliferate across a branched state space. We must finally reconcile how the smooth topological manifold of general relativity emerges from this discrete Planck scale network. The UV completion is a hydrodynamic-style coarse-graining procedure performed over trillions of decohered microgeometries. Averaging these discrete fluctuations yields the smooth line element of the metric tensor, matching the Einstein tensor at macroscopic scales. Under the Wheeler-DeWitt equation, the universal wave function is a stationary state. The Wheeler-DeWitt equation is a mathematical framework in quantum cosmology that implies time does not exist as an external variable. Gravity functions as a thermodynamic equation of state rather than a propagated signal. The persistence of gravitational forces is the predictable, static correlation between adjacent configuration slices and an unmoving universe. This finite counting measure of slice density allows for a reevaluation of the origin of the universe. Since slice density is an integer count of discrete configurations, a literal infinite density is mathematically impossible. The Big Bang is redefined as a rigid bottleneck in configuration space, where branching multiplicity is minimized at the Planck scale. VSD suggests the testable hypothesis of paleogravity, where the fundamental gravitational constant might shift over cosmological eras as the baseline slice density evolves. By treating spacetime as an emergent tapestry of quantized geometric data, VSD preserves the predictive geometry of Einstein while taming the microscopic infinities that broke it.